Okay, today we're starting a new unit on probability. We're going to go through a couple different lessons today, and I'm just going to kind of skim through it because most of this is either you've seen it in the past or it should come fairly natural to you. So we are going to go over a couple different vocabulary words. On 6.1, it's all about sets, subsets, and Venn diagrams. So the vocabulary involved with that is an event is an activity or experiment, which is usually represented by a capital letter. A sample space is the set of all possible outcomes for an activity or an experiment. A smaller set of outcomes from the sample space is called a subset. So the the sample space is what the set of all possible outcomes are. But a subset is just smaller, not as many outcomes handpicked from that sample space or from that set. It's a subset, it's smaller. The complement of a subset is all the outcomes in the sample space that are not part of the subset. Okay, so if I have the numbers 1 through 9 and I choose a subset of 1 through 5, then that's my subset 1 through 5, but my complement would be all the numbers not 1 through 5, so it'd be 6, 7, 8, and 9. Okay, so it's all the possible outcomes that are not in the subset. A subset is if A is a subset represented by A, the complement can be represented by any of the following. The first one is an A with a little C in the corner, stands for complement. The second one is an A with a little line there. And the last one is this little squiggly and then A. Stands for not A, which is the complement. Okay, then the union of two events includes all the outcomes from each event. The union can be indicated by the word or can be indicated by the symbol, looks like a U. It's a union. Okay, so the union is all the outcomes for any two events. It can be just the outcomes of A, just the outcomes of B, or it can be the outcomes of A and B. So it's anything that's in our events is in the union. The intersection of two events includes only those outcomes that occur in both events. The intersection can be indicated by the word and or the symbol that looks like an upside down U. If the two events do not have anything in common, the intersection is the empty set. That's indicated by empty brackets or this little zero with a line through it. Okay, that's the empty set. It's a set that has no values inside of it. Okay, looking at example 1, we're supposed to complete the Venn diagram with the following. The sample space is green, violet, turquoise, yellow, blue, red, white, brown, peach, black, magenta, and orange. Okay, so our Venn diagram, it's got primary colors over here, American colors, American flag colors over here, and then the inside would be the overlap. What's a primary color and an American flag color? Okay, so that's the part I always like to do first. What colors do I have that are both primary and American flags? Well, out of the primary colors, we've got blue, red, and yellow. And out of the American flag colors, we've got blue, red, and white. So both a primary color and an American flag color, red lives there, that has both of those, and blue is both a primary color and an American flag color. Now we just got to finish this out by saying what other primary colors are there. Well, yellow is a primary color, but it is not part of the American flag colors. And white is a part of the American flag colors, but is not a primary color. So then that would mean that all of my other words are going to go on the outside of this. So we still have to include all these other colors like orange and brown and peach, but they don't go anywhere inside of these circles. They're going to go somewhere on this outside here. So over here, I'm just going to go orange, magenta, green, violet, turquoise, brown, peach, and black. Okay, and now I should end up with 12 colors, and I do. Okay, so now my Venn diagram is complete. It says the subset of primary colors. Now I need to write down the subset of primary colors. Well, primary colors include red, yellow, and blue. So that would be my subset of primary colors. Now my subset of the American flag colors would be red, white, and blue. Okay, now it's going to ask a couple questions. It asks for P union A. So P being my primary colors and A being my American flag colors. So what is P union A? Well, if we remember, union is all the outcomes from each event. Okay, so that's going to be anything in the primary colors, anything in the American flag colors, and anything in the middle. Okay, so I'm going to write down all of these colors. We've got yellow, we've got red, blue, and white. That's our union. And down here, it asks for the complement of P. So anything not in P. Well, P just has these three colors, red, yellow, and blue. So the complement of P is going to be green, violet, turquoise, white, brown, peach, black, magenta, orange. Instead of writing all of those down, I'm just going to say not P. But if I were going to actually write it down, I'd have to write down all those colors I just listed. Okay, now over here, it asks for the primaries intersecting with the American flag colors, P intersect A. So what do they share? Well, both of them have red and both of them have blue. So I can say red and blue, which I can also see by looking at my Venn diagram up above. The intersection, or the part they share, is red and blue. Okay. Now remember, this symbol is a little knot. So I'm looking for the complement of P union A. So the complement of P union A would be everything that this isn't. So again, it would be a lot of these colors up here. So I'm just going to skip it. But if I were going to do this, I would write down all of those colors. Okay. Now we are going to turn the page and go to example 2 here. We're going to skip example 1 and jump to example 2. Given the sample space S, which is 0, 1, 2, 3, 4, 5, 6, 7, 8, 9, and the event A, which is 3, 4, 5, 6, 7, and B, which is 1, 2, 3, 4, 5, we're supposed to draw the Venn diagram representing A and B. Okay, so I'm going to label 1A and 1B. And now I've got to fill in this Venn diagram. So I need to put in what they share in the middle here. So what does A and B share? Well, if I'm looking at A here, they share, and looking at B, 3, 4, 5 looks like are in both of these. So I'll put 3, 4, 5. And then I'll cross those out to signify that I've already used them in all of my sets. Okay, now if I'm looking at just the things that are left over in event A, I've got 6 and 7. So I'll put a 6 and a 7 in here. I'll cross those out. And if I'm looking at the events left in B, I've got 1 and 2. So cross those out and put them in B. And cross them out up here. And now that I have A and B completed, I need to put everything that's not in A and B, which is 0, 8, and 9. So 0, 8, and 9, I'll put out here. 0, 8, 9. And I'll cross those off as well. So now I've used all of the numbers in my sample space, and my Venn diagram is complete. Okay. So now I need to find A union B, or A and, or sorry, excuse me, A or B is how we would say that. A union B or A or B. So A or B is all the events in both A and B. So it's 1, 2, 3, 4, 5, 6, and 7. It's everything in my Venn diagram in the circles. So I'll say 1, 2, 3, 4, 5, 6, and 7. Now for A intersect B or A and B, it's just where they overlap. It's just this middle part, what they share. So this one is just 3, 4, 5. And then for the complement of A, it's everything not inside of A. So it's all of these numbers out here, which is 1, 2, 0, 8, and 9. Everything not inside of that A circle. Okay, now we're going to skip example 3. We're going to skip example 4, skip example 5, skip example 6, skip 7, skip 8, skip 9, and we're going to jump to 16.2. Okay, we're going to talk about the fundamental counting principle. The fundamental counting principle is when I have different independent events and I want to find the total amount of outcomes for those different independent events. So it says you can use the counting principle to find the total number of outcomes if one activity can occur in m ways and another activity can occur in n ways, then both of the activities can occur in m times n ways. Okay, so what that's basically saying is when I have those independent events, I just multiply their numbers together and that gives me my total amount of outcomes. So let's look at some examples because this sounds super confusing, but it's actually very straightforward. Okay, so it says the ice cream shop offers a choice of 3 cone sizes, 15 flavors, and 8 toppings. How many cones are possible if you can only choose 1 flavor and 1 topping? Okay, well, I'm just going to look at each event independently. If I'm looking at how many cones I have, I can choose between 3 different sizes. Then if I'm looking at how many different flavors I have, I've got 15. So I'm going to go 3 times 15. And then if I'm looking at how many toppings I have 8. So I'll times that again by 8. Each of those does not depend on the other. The size of cone I choose doesn't mean I have to choose a specific flavor. I can choose any of them independently. So if I do 3 times 15 times 8, I get 360 different cones that I can make. Okay? And that's all this fundamental counting principle is multiplying our numbers together. So it says a quarter is tossed, then a letter from the word snowflake is chosen. How many outcomes are possible? Okay, well, if I toss a coin or a quarter, I can either get heads or I can get tails. So I have 2 different outcomes that come from it. And then if I choose a letter from snowflake, well, snowflake has 9 different letters in there. So I can choose any of the 9 letters. So 2 times 9 is going to give me my total possible outcomes, which is 18. Okay. On the next one, Patrick is buying a new car. He can choose the body style, the color, and the engine type. There's 54 ways he can select a car. With 3 body styles and 2 engine choices, how many colors are available? So now it tells me my total number of outcomes. It says that my total number of outcomes is 54. I've got 54 different ways we can select a car. It tells me that I've got 3 body styles and I've got 2 engine choices, and I need to figure out how many colors are available. So I have 3 times 2 times a variable C that represents my colors. And now I just need to get C all by itself. So this looks like 54 is equal to 3 times 2, which is 6C. And then to get C all by itself, I'll divide both sides by 6. And that'll give me that 9 is equal to C. So I have 9 different colors available. Okay. I'm going to skip this box and I'm going to jump to factorials real quick. Okay. So factorial, which looks like an exclamation point, is the product of all natural numbers from highest to lowest. Okay, so what that means is if I have 9 factorial, like written here, what 9 factorial means is 9 times 8 times 7 times 6 times 5 times 4 times 3 times 2 times 1. Okay, so it starts at 9 and it goes all the way down to 1. Now, if I put 9 factorial in my calculator, I get 362,880. If I put 9 times 8 times 7 times 6 times 5 times 4 times 3 times 2 times 1 in my calculator, I also get 362,880. Okay, so this factorial is just a shortcut. Because if I'm trying to put in a really big number like 100 factorial, it would take me forever to type all of that out. But I can just put 100 factorial and it would just take me a couple seconds. So the factorial button is found on your calculator. There's a PRB button. You push PRB, and then I believe it's the third option. So you push, like if you were going to put 9 factorial in, you push 9, and then PRB, and then 3. And that'll give you a little exclamation point, which means factorial, and then you'll push enter. Okay, if we put 12 factorial in the calculator, we get another big number here. I think 479, comma 001, comma 600. Okay, so that's just 4 factorial. It's that big of a number, or sorry, 12 factorial. So as you imagine, as we get bigger and bigger, these are going to become very large numbers. Okay. 8 factorial is going to be a bit of a smaller number. It's going to give me 40,320. And I can also put something in like 17 factorial divided by 11 factorial. And that will simplify down to 8,910,720. So all of these we're just plugging into our calculator with the factorial button. Now the one exception to this rule is 0 factorial. So normally I would start at my number and I'd go down to 1. But 0 is already less than 1. But we do have an exception for 0 factorial. It doesn't equal 0. 0 factorial equals 1, and it always equals 1. That's just something that we'll need to remember, or if you do forget, you can put 0 factorial into your calculator, and it'll tell you that 0 factorial equals 1. Okay, and that's where we're going to stop with notes today. We do have a Delta Math assignment online. And thanks for watching.